You can have an integral. All right, so it says a Plato loop is consisting of a single turn across the area is 100 centimeters squared, which is boop, boop, so it's 0.01 meters squared. So picture that first. It's perpendicular to a magnetic field that increases a uniform magnitude from 0.5 to 2.5 teslas in a time of 1.5 seconds. So what is the resulting induced current of the coil? The total resistance of 4 ohms. So I go V equals d dt, BA cosine theta. Cosine theta is not changing, it gets out of there. Boom, done, out of there. It's going to be 1, right? Magnetic field is changing. What's the area? Area is not changing, it's 0.01. So we go d dt of B. What's the rate at which my magnetic field is changing?
Is that dB dt?
dB dt, yes. So what's the rate at which my magnetic field is changing? It's going up 2 in 1.5 seconds. Is that right?
Yeah.
So that's 4/3.
Oh.
So I slap a 4/3 into here, and I get, whoops, 1.3, so 0.0133 volts is my potential difference. And I turn that into an IR. My R is 4. Multiply by 4, I get 0.06.
Divide by 4.
Divide by 4 would be better. And that's not what I was doing, so I'm glad you pointed that out. What I get?
Negative 3. 3.33.
3.33 times 10 to the negative third amps.
Why did you just take the derivative, or why didn't it entirely go to 0? Not entirely, but why didn't the 0.01 and the 1 go to 0 when you take?
Because their numbers multiplied.
Oh,
Now, if all 3 were constants, then what would happen to my derivative?
all 3 of them were constants, then it would just become 0.
Then it becomes 0, which means if you're not changing either your B, your A, or your angle, you have no voltage and magnetic field. There's no magnetic field generated, right? So therefore, there's no current, right? If none of those things are changing, there's no voltage generated. It's the wire is perfectly happy to keep doing what it's doing. That make sense? All right. Try number 2.
Can you read it?
A coil formed by wrapping 50 turns of wire in the shape of a square is positioned in a magnetic field so that the normal to the plane of the coil makes a 30-degree angle with the direction of the field. Okay, so normal 30 degrees. Okay, so we're off normal. It is observed that the magnitude of the magnetic field increases from 200 microteslas to 600 microteslas in 0.4 seconds. An EMF of 80 millivolts is induced in the coil. What is the total length of the wire? Bum, bum, bum! Voltage. So this time it's going to be cosine of 30 degrees, because it's darn close, right? Area they gave us, we don't know. Magnetic, but it's not changing, which is important. The magnetic field is going from 600 times 10 to the negative 6 to 200 times 10 to the negative 6 in 0.4 seconds. So that's 400 times 10 to the negative 6 over 0.4, which is like 4 times 10 to the negative third when I get done with all that mess.
What? I got 1 times 10 to the negative third.
Oh, 1 times 10 to the negative third, you're right. The 4 is dead, you can't look for it. So 1 times 10 to the negative third. And then they tell me the voltage is this, but I gotta be careful because it's the total voltage, right? And they wrapped it into 50 loops. So 0.080 is my voltage, but I got 50 loops. So I'm actually getting 0.016 volts per loop. So 0.016 times 0.016 equals 1 times 10 to the negative third times the area of a loop times cosine of 30 degrees, which is 0.866. Give me 15 times to figure out how to graph these calculators. Stinking TI. I do. I can't find any of them, which is great.
There's one over there.
Yeah, so that's good. That doesn't graph though. It's not a graphing one. I got the area of my loop is really big. Has anybody got a really big number? I got
Well, that's volts per loop.
18.5 is the area of my loop, right? Is that right?
Oh, I got 0.184.
All right. What did I do wrong? A stinking Casio. No, that's good. No, that's good. No, I look legit.
Because I. Hold on.
Am I right?
Yeah.
It is wrong.
Oh wait. Oh.
Let me help me out.
No.
Is it Singleton 18.5?
I matched those.
Okay. So if that's the thing, then the size of it would be 0.5, which would be 4.3-ish with the length of a side. Sorry, what? Which way?
Say that last thing.
Because if that's the area, then the length of a side, because it's a square, if it's 18.5 is my area, each of the side has to be 4.3 to make that work.
The area is 1.8.
Okay, so we've got a problem with our numbers
It
here.
should be when you divide. Or not even divide.
That's right. Okay, so it should be -4. Then -3 when I get done. So I got 1 times 10 to the third. I like your answer better. That's why I'm trying to work real hard to get it.
Try plugging it in again.
Where you got 1 times 10 to the third, right?
Yeah.
For the over there. For the change,
Yes, that's fine.
that's the change 1 point, and then you have to multiply by 0.86x.
Yeah.
We got the voltage per loop was 0.01516. Is that right?
It should be another 0 there.
Wait,
Another zero
did they
there?
give you the voltage?
That should be 80 x 1 but,
1, 2. Yeah, you're right. Should be another there. There's it. That's where it is. Got it. Okay, so we're catching up to you. So this is 1.85, which makes this 0.43, probably. 1.85 to the 0.5. Nope, I'm a complete liar. This is 1.36 length of side. And then that times 4 times however many loops we have. 50 again?
Yeah.
Total.
That should be the total length of the wire. Yeah, yeah. Well, that's 200 times that, so times 200. And I got 272 meters.
Oh, it's the box.
Okay, so what I did was I used the voltage that they gave us,
Mhm.
and when I got my area, I divided that by 50. Is
Okay,
that still
That's fine. Should
What's
work.
that character in between the 1.36 and 50?
Multiplication. Oh, 4. There's 4 sides of the square.
Did you bring all
All
those
right.
coils up?
Try number 3. Okay, so I've got circular radius of 0.05 meters, which makes my area equal to pi 0.5 squared, which is 0.0025 pi. Is that right? You guys decimalized it. Is that right?
I just left it as pi 0.05 squared.
Okay, that'll work. Okay, moving forward. I got this. It says direction of the magnetic field varies according to the expression B equals that. So I'm changing my B, right? So I'm going to go ddt, my voltage, or my potential difference, is equal to BA cosine theta. Magnetic field's what's changing. Everything else can go out in front. So I get 0.05 pi, that's squared, that's not, times the cosine theta. I assume this is perpendicular to the plane, so this is going to be a big whopping 1. So d dt of the thing they give me is 0.02t plus 0.05t squared. Are they asking for a specific time? Yep. So I got to do it at the very end. Okay, so I grind this up. I get 0.0025 pi times 0.01 t squared plus 0.05 over 3. I'm taking the intervals. That's not what it's supposed to be doing.
I got that in his head.
0.02 plus 0.10
He got that.
t. All right. And then I'm just going to plug a 0.6 in there, and I've got it, or 6 seconds in there.
And divide by 20.
And divide by, multiply by 20, probably.
That's
20 current, so yeah, so I'm going to multiply by 20 to increase the voltage.
okay. So I was doing had it right, but
So 0.6, this becomes 0.0025 pi times 0.62. And I don't know what that is, but it's a number bigger than 3. No, it's not. Smaller than 3. Then come with a new phrase. 0.0025 shift pi times 62 divided by 100 is the lovely 0.00487. That's per loop times 40 loops. Is that what it is? 40 loops? 20. That's 20 loops. Times 20, I end up with an EMF of 0.0974 volts. Is that right?
I got 0.1.
0.10. Probably been around than I am. Cool beans? Makes sense? Can do it all day, Jade?
Yeah.
All right, let's flip this over. She just went to the bathroom, didn't she?
oh, you're done.
Spite me. Well,